The last thing to cover for Chapter 9 is going to be to go over how to use bond dissociation energies to estimate the enthalpy changes for gas phase reactions. So if you think back to when we talked about covalent compounds and I introduced the concept of a covalent bond, we discussed what determines the equilibrium bond length between two atoms. And it's the point at which the separation between the atoms minimizes the potential energy between the two atoms in question. Now, that potential energy is the same amount of energy that's required to break apart the atoms in that bond. So bonding is a favorable interaction, which is why it takes place in the first place. So it takes a certain amount of energy, usually a relatively large amount of energy, to break bonds apart. So the process of breaking bonds is an endothermic process, and the process of forming bonds is exothermic. Now, we have tabulated values, some of them exact, some of them are averages of many different compounds, for bond dissociation energies for covalent bonds between many different elements. Now, this depends both on what the two atoms in question are, as well as the type of bond. So for instance, if we look at some carbon-carbon bonds in this table, which I will highlight, you can see a carbon-carbon single bond has a bond dissociation energy of 350 kilojoules per mole. And that's not really all that close to the bond dissociation energies of, say, a carbon-carbon double or a carbon-carbon triple bond. Remember, when we talk about covalent bonds, shorter, stronger bonds have higher bond dissociation energies. So double bonds are stronger and shorter than single bonds. Triple bonds are shorter and stronger than double bonds. And as such, as the number of bonds increases, so does the bond dissociation energy, the amount of energy required to rip those two atoms apart. So we can use values in a table like this to help us estimate what the enthalpy change is for a reaction if we know how bonds are being formed and broken in terms of converting from the reactants into the products. So as a relatively straightforward example of this, we can use the reaction of hydrogen gas and chlorine gas to form 2 mole equivalents of hydrogen chloride gas. Now, since everything is in the gas phase, that allows us to use bond dissociation energies to not calculate the exact enthalpy change, but at least estimate it. So for the most part, you can only estimate enthalpy changes based on this. Now, to be able to use the values from the previous chart to come up with our enthalpy changes, we essentially need to know what kind of bonds we're dealing with. So for hydrogen, H2 gas, we of course have 2 hydrogen atoms with a bonding pair of electrons in between them, and that's really all there is for hydrogen. For chlorine gas, we have a chlorine-chlorine single bond. And of course, in the case of chlorine, like any halogen, when it's a diatomic element, it's going to have 3 lone pairs on each of those atoms and a single bond between them. Now, the product that we're forming, HCl, in the gaseous phase is a covalent compound, and that consists of a hydrogen atom with a single bond to a chlorine atom. And that chlorine atom is going to have 3 lone pairs of electrons on it. Now, remember, bond dissociation energies are endothermic, and they refer to the energy change associated with breaking bonds. Now, what we're doing is we're essentially forming bonds between hydrogen and chlorine in hydrogen chloride gas. So our equation for using these bond dissociation energies to estimate the enthalpy change for this reaction is kind of the opposite of how it works for, say, enthalpies of formation. Specifically, we need to add up the bond dissociation energies appropriately for the reactants, and then we're going to subtract the same for the products. Remember, with the enthalpy change for a reaction based on heats of formation, it was products minus reactants. Here we have reactants minus products, and again, that's just due to the fact that we're dealing with bond breaking energies when ultimately this reaction is we're forming bonds, essentially. So our reactant bonds are our chlorine-chlorine single bond and our hydrogen-hydrogen single bond, and our product bonds are our hydrogen-chlorine single bonds. Now, there's a couple of things to take into account here, which is how many of these bonds do we have per molecule, and how many moles of each substance do we have. That latter thing also shows up when we're dealing with, say, heats of formation, but when we're dealing with larger molecules, we need to account for how many actual bonds there are in each molecule as well. In the case of all of our reactants and products here, each molecule just contains one bond, and so we don't need to multiply by any further coefficients. If you look up the bond dissociation energy for chlorine, that's going to be 243 kilojoules per mole, and for hydrogen, it ends up being 436 kilojoules per mole. And we have 1 mole of each of those substances in the reactant side of our balanced equation, so we add those two together, and from that we're going to subtract the bond dissociation energy for a hydrogen-chlorine single bond, which if you look that up in your textbook is 432 kilojoules per mole, and since we have a coefficient of 2 in front of that in the balanced equation, we're going to multiply that by 2. And so when you plug in all the values, we end up with an enthalpy change estimated for this reaction of negative 185 kilojoules. And that turns out to be pretty close to the experimental value.